Hello everyone, here Rodrigo is speaking, and today we present my paper entitled A Model-Based Approach for Analyzing Network Communication Timeliness in IMA Systems at Concept Level. The paper was written by myself, my co-authors Simona and Simin. Simin and I are with Linköping University in Sweden, and Simona is with the University of Zaragoza in Spain. So, a little bit of background on what led us to write this paper. Linköping is a city south of Stockholm in Sweden, and it's the home of the aviation division of Saab, which produces this plane here you can see in the picture, among others. This proximity to the industry actually gives us some insights about what's going on the aviation industry. And one of the things we saw during the last few years was the change from the federated to the integrated modular avionics paradigm for avionic architectures. So in the federated architectures which were used in the past, software processes were allocated to CPUs and the rest of the architecture were built around this allocation. So this type of paradigm is not very flexible since we don't have the possibility of adding new functionalities or moving the processes around in order to do that. So to deal with this problem, the market shifts towards the integrated modular avionics paradigm, in which processes are allocated to the CPUs, but we have way more flexibility in moving those processes between the CPUs and adjusting for the opportunity of developing new products or create product changes during the life cycle of the airplane. So it's very important here to think about how the architecture supports the execution of these processes, which we should do at the earliest stage possible in the development processes to avoid further costs in the future. So we do it in what we call the concept level. And let's talk a little bit now about how to verify that this is the case during the concept development process. So during the early concept development phase of the development process, what we have is an early description of our avionics application. So we have the software functional elements and we have a little bit of application requirements which are relevant at this point. And based on this skeleton of the functional elements and the requirements, the engineer actually comes up with an early platform configuration. So nothing too detailed, but just ideas about network topology, which type of protocols will be used, what network bandwidth will be used, how processes will be allocated to the CPUs, which security and safety measures will be adopted in this platform. And then, taking the functional elements and their platform configuration, we actually create a platform performance model, which we check against our application requirements to see if the platform can support the application. So this last part is exactly where the scope of our work here is. In this paper specifically, we'll be focusing on creating the platform performance model and analyzing it from the network adequacy requirement perspective. So if the choices about the network, the topology, and the bandwidth help support the application requirements. So to do that, we actually propose a workflow on our paper. This workflow is composed of 5 main actions. The first action is modeling the IMA system in UML MARTE, which is done by the industry actor or the concept engineer. Then the engineer feeds these UML MARTE models to our tool, which translates them to a network calculus representation. Network calculus here is the analysis technique we use to analyze the network itself. So I won't get much into network calculus, but it's basically a fast method of calculating end-to-end delay bounds in networks. So after the translation, we have the analysis. So the network calculus analysis tool actually analyzes this network calculus representation and returns end-to-end delay bounds for each of those message types into our tool, which we then check and verify against our set of requirements and present the results back to the industry actor or engineer. The engineer then decides if he or she satisfied with the results of this verification. If yes, then we are done with the process. If no, then they can make changes to the platform and adjust them so that it fits their needs. So far, we've been talking about IMA platforms. So let's see what this platform actually look like. So in this paper, we consider an IMA platform composed of 3 levels. The first level is composed by the processing elements. So in this level, we have our CPUs, our GPUs, and other hardware devices capable of computation. Residing on these hardware devices, we have our software processes. Here on this picture, the software processes are represented by the circles named P1 to PM, and each of these software processes exchange messages with other software processes within the same CPM or residing on another CPM. So in order to provide this inter-CPM communication, each CPM has associated to it a network interface. Here, these network interfaces are called end systems, and each end system is composed of 2 parts, a receiving part and an ending part. These end systems in turn connect to the underlying network infrastructure, which defines the network through which messages will travel, and this network infrastructure can be composed of switches, hubs, and other hardware network elements. So, based on this platform I just described, we have identified the important aspects of the platform and of the hardware elements that are relevant for the verification of network resource adequacy analysis at this concept level. So things such as the periods of the processes, the size of the messages, the bandwidths and latencies of end systems and switches, and things like topology of the network. This domain model we propose here is then used to support engineers on the creation of the UML-MARTE models we propose on our workflow. So what do these models actually look like? In the paper, we propose to use deployment diagrams from standard UML to represent the architecture configuration, so capturing things like the network topology, which processes are allocated to which CPMs, and how these CPMs connect to other network elements, for example, switches. So the idea here is that these important and individual elements, such as CPMs and the processes themselves, are represented by standard UML diagram elements, and to each of these elements, we can apply a stereotype from the MARTE library and annotate this stereotyped element with the relevant attributes, for example, such as the periods of the processes and the bandwidth of the end systems and switches. As an example, here we can see the usage of an UML artifact to represent a software process. To this artifact, we have applied the assay step stereotype from the MARTE library, and we have used the interoccurrence times and execution time attributes from the MARTE library to represent the period and worst case execution time of the process respectively. So similarly, we propose the usage of communication diagrams to represent how each process interacts with other processes. So here the idea is to capture which message comes from where and goes where, and also the sizes of these messages that are exchanged by these processes. So once we have this UML-Martin model defined, we go into what our tool actually does. So these UML-Martin models are fed into our tool, which transforms these models into network calculus models of the network and analyzes these network calculus models using the integrated network calculus analysis tool, outputting the end-to-end delays each of these messages is subject to. Once we have these end-to-end delays, we can actually compare these end-to-end delays to the requirements we define from our models, and then we obtain the verdict of whether the proposed platform configuration can or cannot support the set of avionic applications we want it to. So, which are these timeliness requirements? The problem here is that extracting requirements at concept stage is a challenge because often there's no information on freshness or timeliness requirements at this point in the development process. So it brings us the question of what is relevant at this stage and what can be obtained from the model and the information we have at hand at this point. That leads us to the definition of one high-level requirement. If new data exists, a process should not work with old data for more than one execution cycle, which implies that data destined to a process should be received within one period of the receiving process. And this requirement can actually be extracted or derived from the models we have and the amount of information we have at this point. So now let's move on and see how can we apply our workflow to an actual industrial use case. So here we use an industrial use case provided by SAB, which is composed by two parts. One FCP, which stands for Fight Critical Part, and one mission-oriented part, which we call MOP. So the MOP part is composed of 91 processes that exchange 629 messages, and the FCP part is composed of 8 processes and 31 messages. For the purpose of illustration, I show you here an FCP example deployment diagram. So the deployment diagram used to represent the FCP part of the use case. Here we can see the 8 processes of the FCP allocated to 4 CPMs, each CPM with its own associated end system, and the network composed of 2 switches, which you can see in the lower part of the diagram. However, this smaller FCP part of the use case is not very interesting to be analyzed due to its small size, just 8 processes. So this MOP part, the second part with 91 processes, is way more interesting to analyze, and that's what we will present here. We will not present the diagrams of this MOP part due to their complexity, but we have mapped each one of the 91 processes to one of 11 CPMs, and we have created 6 different platform configurations with 3 or 4 switches and different bandwidth for network elements in order to verify if these different configurations actually comply with our requirements. We have also assumed that the switches and end systems introduce a latency of 1 milliseconds to the path of the messages that go through them. So by applying our workflow, what we have found out is that only architectures or platform configurations that have elements for which the bandwidth is 1 gigabit per second actually support our avionic application, meaning don't delay the messages too much so that processes have to work with old data. So now let's move on to our conclusions and the main takeaways and lessons learned from this paper. We have presented a model-based approach for the verification of resource adequacy on IMA platforms. During the process, we found out that it's very important to describe the problem at hand at the right level of abstraction and avoid complex models or too fine-grained models that are hard to understand and hard to communicate or to discuss about. We have also found out that it's important to have reusable models suitable for future reconfiguration in case new functionality needs to be introduced to the system in the future. So for our future works, we are currently working on extending the model to consider other non-functional properties such as security, safety, and energy consumption. And of course, we are going to apply the same type of analysis to these different non-functional properties to verify if they actually support the avionic applications we want to run on these candidate configurations. So that leads us to the end of our presentation. Thank you for listening, and we will be open to questions during the conference.